Welcome viewers, in this video we'll see the details about the parallel resonance. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic parallel resonance. Consider this parallel circuit. In one branch R and L is connected, in another branch R and C is connected. So this is the supply voltage. So AC supply is given. The two terminals X and Y. In the first branch, resistor and inductor is connected, R1L. In second branch, resistor and capacitor is connected, R2C. Now we'll go for the analysis. The total admittance is equal to Y equal to YL plus YC. YL means the branch connected with inductor. YC means branch connected with capacitor. So this admittance is nothing but reciprocal of the impedance. So YL can be written as 1 divided by ZL. Similarly, YC can be written as 1 divided by ZC. Right? So this is the impedance in the first branch with L, R and L. Impedance in the second branch with R and C. So this ZL in the branch 1 can be written as R1 plus JXL. Similarly, in the second branch R2 minus JXC. Right? R1 is available in the first branch. Inductor, the impedance is XL. R2, because of capacitor, we have minus JXC. Right? So this is branch 1 impedance, branch 2 impedance. Now we'll take this equation number 1. In order to, here the J term available in the denominator. In order to make the available in the numerator, we are going to multiply and divide by the term, so that we can brought the L term in the numerator. So this first term 1 divided by R1 plus JXL is multiplied with R minus JXL divided by R1 minus JXL divided by R1 minus JXL. So while dividing, the original will not be affected. It is divided and multiplied and divided. Similarly, this R2 minus JXC is multiplied with R2 plus JXC divided by R2 plus JXC. Here plus is there, so minus. Here minus is there, so plus. Why we are doing like this? This J term available in the denominator. If you multiply this, is called a complex conjugate. The J term will appear in the numerator. Now we'll go for the simplification. R1 minus JXL. This is nothing but A plus B into A minus B. That is nothing but A square minus B square. A is R1, R1 square minus B is JXL, J square XL square, plus this R2 plus JXC divided by, this is also A plus B, A minus B. So A square, R2 square minus J square XC square. Right. So R1 minus JXL divided by R1 square. This J square is minus 1. Similarly, here J square is minus 1. So due to happen, this negative with negative become positive. Here also positive. So R1 minus JXL divided by R1 square plus XL square. R2 plus JXC divided by R2 square XC square. Now we are going to split the terms. This is a real term and this real term and complex. This is a complex conjugate, real term and imaginary term. We are going to split the terms. Now we'll see how to split the terms. So now it is splitted. R1 divided by R1 square plus XL square minus J XL divided by R1 square XL square. This term is splitted. So here also it is splitted into 4. Now we'll combine the real term. These two are real term, these two are imaginary term. So we'll combine these two terms. We'll take the J outside, right? So that this XC divided by R2 square XC square. Here minus is there, is written in the next second term. First term, this term is written first, minus this term because of minus J. Right. Now we have the impedance. This is a total admittance. We got the expression. See this, now J is available in the numerator. So that we are multiplied with complex conjugate. Right. Now in this is the real term. This is imaginary term. At the resonance, the reactive part is 0. Part of Y is 0. So we are dealing with the parallel resonance. At the resonant condition, this reactive part means this imaginary part is 0. bring this term that side, so this negative become positive. So xc divided by r2 square plus xc square equal to xl divided by r1 square plus xl square. Now we'll go for the further simplification. So these terms are cross multiplied. So xc is multiplied here, xl is multiplied here. We note that xc is 1 divided by omega naught c, the resonant frequency. Similarly, xl is omega naught L, right? So these two terms are now. Now bring this omega naught and c in that side to the numerator. So that is omega naught c, omega naught L, and this term. This omega naught available 2 times, omega naught square LC, right? Now multiply this term inside. So omega naught LC into R2 square. Here omega naught LC divided by omega naught square into C square. So what happened here? This omega naught square got cancelled. C one term got cancelled. So R1 square plus omega naught square L square equal to omega naught square R2 square LC plus here one L is there, here one C is there. L by C. L by C is there. Now we'll go for the further simplification. This R is brought that side and this omega brought this side. So that we'll combine this omega terms one side and other terms one side. So omega naught square into L square minus this term is brought here, omega naught square R2 square LC equal to L by C minus R1 square. This term is brought that side. Right, now take the omega naught square outside, commonly available. L square minus R2 square LC, that is equal to L by C minus R1 square. Right, here we'll take the LC outside. Only L is commonly available, but here we'll take LC outside. Right, so here LC is taken out, only R2 square. Here L square is there, so one L is taken outside, so that L divided by C not available, so divided by C. That is equal to 1 by L by C minus R square. Now bring this term in the denominator, denominator that side. So that will got omega naught square. L by C minus R1 square divided by LC into L by C minus R2 square. I will go for the further simplification. So this L by C, this is 1 divided by L by C. Here what is available is written in the reverse, it is interchanged, R1 square minus L by C here, so that will get one negative. This term also interchange, so here also get one negative, so both become positive, R2 square minus LC. In order to bring the uniform form, this R is and these two terms are interchanged. While interchanging, this term will get negative, this term one more negative, so it become positive. So this omega naught square. So omega naught is nothing but you have to take the square root on both the side. 1 divided by square root of LC into square root of R1 square minus L by C divided by R2 square minus L by C. So this is the resonant frequency. So in this video we discuss the parallel resonant. At the resonant condition, what is the frequency? The two branches available. In one branch, resistor and inductor is connected. In another branch, resistor and capacitor is connected. We calculated the admittance and equated the reactive part equal to 0, so that we got the expression for resonant frequency omega naught. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.